Hello and good morning. I'm Tony Truelove, and I'll be your moderator for today's webinar. Welcome to our first Engage the Experts webinar. This series of webinars will give you more insight into diesel cylinder deactivation, which is a key to achieving future diesel emissions. Each webinar will delve into various aspects of CDA. And as you can see from the presentation here, this week's webinar is titled The Truth About Diesel CDA and NVH. Our experts will discuss the extensive testing to evaluate engine and after-treatment performance, along with engine vibration over 8 drive cycles in a dynamometer test cell. You will learn about the strategies to negate NVH while implementing CDA as a key emission reduction and fuel-saving solution. This presentation is based on the International Journal of Powertrain paper, Vibration and Emissions Quantification over 8 Key Drive Cycles Using Cylinder Deactivation, and it's written by our panel of speakers. The pre-published paper is available now and can be purchased at enderscience.com by clicking on the globe icon and sending them an email. The paper is also scheduled for inclusion in Volume 9, which should be available later this year, around November. Now I'd like to introduce you to our panel of experts. Chris Sharp is an Institute Engineer at Southwest Research Institute. Chris, tell us about the significance of the work in this paper.
Thank you. I've been working on the low NOx technology demonstration efforts for about the past 6 years, and one of the key things that's come out in trying to meet the twin goals of lowering NOx emissions at the same time that we're trying to meet greenhouse gas targets and reduce CO2 is that it really takes a whole system approach to the engine and after-treatment system integration in order to achieve both targets in as efficient a manner as possible. And during our more recent Stage 3 demonstration work, cylinder deactivation has really been a key technology lever to enable us to try to reach those goals and to lower NOx emissions substantially without suffering any greenhouse gas penalties, or in some cases getting an improvement in CO2. And really the reason behind that is that CDA is one of those kind of swing technologies that allows us to either leverage it to do thermal management for the after treatment or leverage it to improve CO2 under light load conditions. So we can really use it to try to reach both goals, and that really makes it a key enabler. But in order for us to use the technology, we've got to make sure that we address all of the key engineering details and challenges necessary to successfully implement it. And really, at the end of the day, for CDA, NVH is one of those key details that we've got to get right in order to reach a successful implementation. And that's really, was at the core of really the importance of the work that we're talking about today. Thank you.
Thanks, Chris. Andrew Matheaus is a senior research engineer in the diesel engine R&D section at Southwest Research Institute, and he performed the testing for this paper. Andrew, tell us a little bit about what you learned.
Thank you, Tony. I just wanted to mention I've tested 2 different engines with CDA over many drive cycles, and I must say the results are very encouraging. Unlike typical methods of increasing exhaust temperature, such as retarding timing or hydrocarbon dosing, CDA provides the temperature increase while also reducing fuel consumption and CO2 emissions in many cases. The increased exhaust temperature at light loads is important to keep the after-treatment system hot and functioning properly, as Chris mentioned. As Tom will discuss in the next section, selecting different CDA modes for varying speed and loads helps keep the NVH in check. Thank you.
Thanks, Andrew. Matheaus Pieczko is a lead engineer in the NVH group at Eaton in Galesburg. Matt, can you tell us how you were involved with this project?
Yeah, thanks, Tony. I'm on Eaton's NVH team, and I, along with Andrew, performed the testing for this data set. I've been supporting our CDA efforts for over 3 years now, so I'm excited we have the opportunity to share some of our results today and look forward to Tom's presentation. Thank you.
Thanks, Matt. And Dr. James McCarthy is Chief Engineer for Vehicle Technologies and Innovation at Eaton. Jim, what were your takeaways from this project?
Yeah, thanks, Tony. Our team at Eaton, we have been working at proving the validity of diesel CDA for approximately 8 years as an essential technology for simultaneous NOx and CO2 reduction. And proving NVH is acceptable has been a major milestone for this work, and we've been working at this for quite a while. So we assembled the right team of people for this project, where we exercised CDA over 8 key drive cycles, and we quantified NVH over all those cycles. I'm very encouraged by this work today, showing that NVH remains nearly equivalent with today's 6-cylinder diesel engine. Tom Reinhart, he's a world-renowned expert in NVH, and I look forward to his talk today. Thanks, Tony.
Thank you, Jim. And our keynote speaker, as Jim just said, is Tom Reinhart. Tom is an institute engineer in the Department of Engine Design and Development and Division of Emissions and Vehicle Research at Southwest Research Institute. Tom previously worked at Cummins and Roush Industries. He leads projects in engine design, performance, and emissions development, as well as in gasoline and diesel engine NVH improvement. Since 2007, Mr. Reinhart has led a number of projects to investigate technologies for improved engine, powertrain, and vehicle fuel efficiency and GHG reduction focused on medium and heavy-duty vehicles. In 2016, Mr. Reinhart completed a project for NHTSA to evaluate the costs and benefits of various fuel efficiency technologies which could be applied to comply with future U.S. truck fuel efficiency regulations. This project formed part of the basis for the EPA and NHTSA Phase 2 greenhouse gas and fuel economy regulations for medium and heavy-duty trucks. He has served on 3 National Academy of Sciences Committee on topics related to vehicle fuel consumption and reduction. Mr. Reinhart has a Bachelor's of Science and a Master's in Mechanical Engineering from Purdue, and he also studied automotive engineer at the University of Hanover in Germany. So as you can see, Tom's got a great reputation as a renowned expert in NVH, and Tom, take it away.
Thank you, Tony. Here's our cover slide, which just describes the title, and you've got the paper number there if you're interested in purchasing the paper from the International Journal of Powertrain. So we're going to cover a little bit of background, talk about some basics of engine vibration, and then look at the effect of CDA on that vibration. We'll describe the test setup that was used in our test cell evaluation, and then the results that we got from the vibration tests on different drive cycles. We'll talk about the importance of avoiding excitation of engine mount resonances in practical applications like in a truck, and then wrap up with some conclusions. So, as I think everybody's already heard, cylinder deactivation is of interest because it gives you the opportunity to do thermal management to keep the SCR system operating at a high NOx conversion rate, while also reducing fuel consumption during light load operation. And by light load, we generally mean at a BMEP of 3 bar or less. Normally, thermal management means you use fuel to make heat in some form, whether that's timing retard, early exhaust valve opening, intake throttling. There's many ways to generate heat, but they all generally tend to lead to an increase in fuel consumption. The question at hand here, though, is that when you implement CDA, you're also changing the vibration signature of the engine, and that's what we're going to talk about today. And then all the data that we're going to describe today was taken on a 15-liter heavy-duty engine in a test cell at Southwest Research. So a little bit about vibration basics. Inline six-cylinder engines are considered good for NVH because they have no unbalanced free forces or moments at the first or second order. And so let me spend a little bit of time explaining what that means. A free force means a force or an alternating force that would cause the engine to move along the X, Y, or Z axis. A moment would cause the engine to rotate about the X, Y, or Z axis. And then orders are basically multiples of engine speed. So an event that happens once per engine revolution is considered to be a first order event. An event that happens twice per engine revolution would be second order, and so on. And so because an inline six has no first or second order forces or moments, the primary source of low frequency vibration in an inline six engine is torque reaction due to cylinder pressure. So as the piston comes up the compression stroke and you hear increasing cylinder pressure, that slows the crankshaft down. As you go over top dead center and back down the power stroke, you're accelerating the crankshaft, and that crankshaft speed fluctuation produces a torque reaction on the engine. And the engine doesn't rotate about precisely any of the three axes, X, Y, or Z. It rotates about the axis of least inertia for the powertrain. So by powertrain, in this case, we mean the engine with all its accessories and the transmission. Basically, anything is bolted together with the engine. And so that axis tends to start high at the front of the engine and come down through the transmission and exit roughly at the transmission output shaft. Is a typical location for the roll axis. And so basically, when you're at operating the engine, the torque reaction will cause the engine to roll about that axis, provided it's not constrained by other things that would force it to move in a different direction, such as the way the engine mounts may be installed. And another thing to keep in mind is that if the cylinder pressure is held constant, then the displacement of the vibration is going to be inversely proportional to speed squared. So as the speed goes down, the displacement goes up rapidly. And that tends to make idle, the lowest speed, the biggest vibration challenge. And it's the biggest challenge for two reasons. One of them is the displacement is largest at idle. But the other issue is that engine mounts have their own natural frequency where the powertrain is the mass on the spring of the engine mount, and you want to avoid having a input frequency that lines up with the natural frequency of the system, because then you'll get an exaggerated vibration result. So now let's look briefly at what CDA does to engine vibration. And so we've got a little table here to try and help make this all clear. The first column is speed, and so we're looking at speeds from 600 RPM up to 1200. And then orders, so 600 RPM divided by 60 is 10 times per second. So the engine rotates at 10 times per second at 600 RPM. So first order is 10 hertz, and 1.5 order is 15 hertz, and so on, up to third order is 30 hertz. And what we care about here is what are the orders that are excited by cylinder pressure to cause the engine to want to roll about its roll axis. And in the normal engine operation, what we're calling 6 CF or 6 cylinders firing, that's the black numbers here. And so you can see that at third order, you have 30 hertz at 600 RPM up to 60 hertz at 1200 RPM. And there are no black numbers at the lower orders. And there's a tiny amount of excitation at every multiple of half order, but these values are very small. And so the only really significant input when the engine's firing normally with all 6 cylinders operating is at third order. The story gets a little different when we go to some of these other operating modes that you can get with CDA. So the red numbers represent 2 cylinders firing. And so when 2 cylinders are active, the firing frequency of the engine is first order. You get 1 firing event per engine rev, 2 firing events per cycle, which is 2 revs. And so you get excitation at 10 hertz at 600 RPM, going up to 20 hertz at 1200 RPM. You also get the first harmonic of that, and so that second order at 600 RPM at 20 hertz, going up to 40 at 1200 RPM. And you get a third harmonic of that, so third order has some excitation. The biggest excitation tends to be at first order. And of course, in six-cylinder operation, you would have multiples of third order. So you get third, sixth, ninth, but those are relatively high frequencies that are very easy for engine mounts to isolate. So we tend not to worry about the higher orders of regular firing frequency. So the next set of numbers is the pale blue numbers, and that's for 3 cylinders active. And so when you have 3 cylinders active, the firing frequency is 1.5 order. And so you see no reaction at first order, but you see a reaction here at 1.5 order. So at 15 hertz for 600 RPM, going up to 30 hertz at 1200 RPM. And then the first harmonic of that is third order. And so you see a response at third order in blue as well. The next option for CDA is to have 4 cylinders active. And that gets a little complicated because there really isn't a clear firing frequency in that event, because you fire 2 cylinders consecutively and then you skip a cylinder. And what happens then is you get a periodic variation in the firing order that occurs at first order. And so 4 cylinders firing looks a whole lot like 2 cylinders firing. You get a first order excitation, a second order excitation, and a third order excitation. And we'll look a little bit more at this on the next slide to maybe provide some better explanation of what's going on. So here's a graphical way to look at engine firing and determine what orders to expect. So this baseline case at the top, where all the red with all the red dots, represents all 6 cylinders being active. And so the period is each firing event, and there's 3 firing events per rev, so we have a third order excitation. If we go down to the next line here, where we've got a blue dot, 2 red dots, a blue dot, 2 red dots, that's 4 cylinders firing. And so you skip an event, you have 2 firing events, you skip an event, you have 2 firing events. And so the period here that's being repeated is 1 revolution. Each revolution you have a skip and 2 fires. And so that gives you a first order response. Alternatively, if you run on 2 cylinders, the next row down, you now have 2 blue dots, a red dot, 2 blue dots, and a red dot. Again, you have a periodic event where you're firing once per revolution, and so you have a first order excitation. And then finally, we have the bottom row, which is the 3 cylinders active row. So we're skipping every other firing event, and our period is now 2/3 of a revolution, or 1.5 engine order. So you get 1.5 firing events per rev, and 3 firing events per cycle, which is 2 revs. And of course, this is all for a 4-cycle engine. This 2-stroke would be a different situation, but we don't have to worry about that in the market today. So what happens when you turn on CDA in the way the cylinder pressure reacts and the way the vibration responds to that? So the plot here on the right shows a situation where you're at time equals 0, you're in all 6 cylinders active, and then shortly after that we turn on cylinder deactivation and we run in 3 cylinders firing. And so you can see that the third order excitation is around 0.7 Gs here in the plot in its normal firing operation. And when you first enter CDA, you get a little bit of a spike, but then it tails off, third order tails off down to about 0.25 or so Gs. And the reason for third order having a decay instead of simply going away immediately when you turn on CDA is what's happening in the cylinder pressure of that deactivated cylinder. What we're doing when we turn on CDA is we trap a charge of fresh air in the cylinder, and there's actually a choice to be made. You can either fire that trap charge by putting fuel into it, or you can just leave it as air. But in either case, when you trap that air, it acts like a spring operating against the piston. But piston rings are not perfect, and so we have blow-by. And so what happens is that some of this pressure then bleeds off into the crankcase because you're repeating operating that spring, that trap volume over and over again. And so the pressure will decay over time. And this is, of course, the peak pressure. The minimum pressure then actually becomes less than 1 atmosphere when you are in CDA mode for an extended period of time. And so if you look at the 1.5 order response here on the top plot, you see that it's basically 0 before CDA is activated. And once it's turned on, you have a constant level of about 0.2, 0.25 Gs that is independent of the decay in cylinder pressure in the deactivated cylinder. So the 1.5 order response is basically just due to the active cylinders. The 3rd order response that is changing with time here is the response of the deactivated cylinders. So in order to avoid a situation where you have very low pressure in the cylinder at bottom dead center in the deactivated cylinder, and you can pull oil up past the rings and increase the oil consumption of the engine, when CDA is active, occasionally the system will recharge a cylinder, pull in a new fresh air charge, and then trap it and keep it there. And so this plot here that says 5 consecutive cycles at idle, that's consecutive recharge cycles. So we've basically let the pressure in the cylinder bleed down, then we inhale a new charge of fresh air and trap it in the cylinder and repeat that. So the blue line here represents the vibration at 3rd order that you would get when all 6 cylinders are firing. The orange line is the 3rd order response when CDA is active, and we've got 5 different recharge events here, so you can see that they're pretty repeatable, where you end up with a little spike right when you first charge the cylinder, and then as the pressure bleeds down, the 3rd order amplitude bleeds down as well. And then the red curve underneath there, which is basically a straight line, is the 1.5 order response. And there's a little bobble here when you take in your new fresh air charge, but other than that, the 3rd order response to the engine is completely flat at just over 0.2 of a G. And then we've got 1st and 2nd order down here at the bottom, and they're very small. And like I said, there's always a tiny multiple of half order. And if you look at engine vibration at low frequency, you'll always see multiples of half order. And that's really just variations in the cylinders that are active. There'll be some that are slightly higher cylinder pressure than others. And that's what gives you this 1st and 2nd order response, which is quite small. So the catch, or the challenge, I guess you could put it, with CDA is that our acceleration levels at 1.5 order, when we're running on 3 cylinders active, is well below the 3rd order level. So let's go back here and look at that again. So here's 3rd order amplitude in Gs, and here's our 1.5 order amplitude down around 0.2 of a G. Whoops, went too far. But there's a couple catches. One of them is that displacements are typically a bit higher with CDA, and that's because of that 1 over speed squared relationship between acceleration and displacement. So the frequency is half as much. So if the acceleration was identical, the displacement would actually be 4 times greater at 1.5 order than it would be at 3rd order. So it's a good thing that our 1.5 order levels are significantly lower than the 3rd order levels. The second problem is that lower frequency inputs are more difficult for engine mounts to handle because you tend to be walking down into the natural frequency of those mounts. as you drop the frequency of your input. So for most applications, you're going to require some level of engineering effort to achieve a desirable solution. And there's two ways you can go about that. One of them is that you can look at changing your CDA modes as a function of engine speed to avoid operating on resonances. And the second is you can look at changing the powertrain mounting system. And particularly here, the goal would be to shift the roll natural frequency of the powertrain down so that you can allow operation with relatively low frequency inputs. So in our test cell setup that we evaluated, we used 4 triaxial accelerometers plus a flywheel speed sensor to get torsional vibration. And you can see in the picture of the engine, here's one towards the front of the engine. Here's one at the very front mount location, another one on the front of the engine, and then one at the rear mount. So this is off of the flywheel housing, and all the mounts went to elephant's feet in the test cell, and they were on soft rubber isolation mounts. Then we evaluated the vibration over 8 different drive cycles that were meant to cover a pretty wide range of engine use, and look at what percent of the time are we below 3 bar BMEP on these different drive cycles, and then what percent of the time do we actually use CDA, and then what mode do we use. So we ran the cold FTP, so the transient emissions test cycle with a cold start, the hot FTP, so same cycle but with a hot start, and there is a difference which I'll show you here in a few minutes. We ran the new light load cycle, which is going to become part of the emissions requirements for California in 2024, and probably for the EPA by 2027. This is an Orange County Transit Authority. I think it's a bus cycle, and then there's a New York City bus cycle, a beverage delivery cycle, the California transient cycle that's used in the EPA GEM model. So when you certify a heavy-duty vehicle, one of the drive cycles that you get is this ARB transient cycle. And another one of the cycles that you get in the GEM model is the 55-mile-an-hour cruise cycle, which does include some hills. So you have a certain portion of the time where you're going downhill and the power demand can be 0 where you're motoring the engine, or it can be very light load depending on the grade. And so then the first column after that is what percent of the time are we running the engine in 6-cylinder firing mode, so the normal engine mode. And you see numbers that range from 82% on the cruise cycle down as low as 28% for the New York bus cycle. And then we look at the different CDA modes. 1CF is a unique mode, so it only operates, so it's basically saying you have 1-cylinder firing, except it only happens when you're motoring the engine. So it's allowing 1 cylinder's worth of air to come through the engine so that you have some air coming through, and that limits how fast you cool down the aftertreatment when you're motoring the engine. And then we have 2 cylinders firing, 3 cylinders firing, and 4 cylinders firing. Those 3 modes are all used when you have some level of fueling required. It could still be a negative torque, but if you need some fueling to maintain that negative torque, and it could be any load up to about 3 bar, which is where CDA gets shut off. And so then the green column here shows the percent of time that one of these CDA modes is active, and then finally the gray column on the far right shows you the total amount of time below 3 bar. And there's the algorithm that controls CDA has a hysteresis, so that when you get to light load and you want to turn the system on, it waits for a little while just to make sure that it's not a very brief excursion into light load. And then when you want to change from one CDA mode to another, there's a slight delay to make sure that the load change is going to stick for a little while before it makes that change. When you want to get out of CDA, when the power demand exceeds 3 bar, it immediately turns off. But there is a hysteresis built into the system here that means that the green column numbers are always going to be a little less than the gray column. So here we're going to have a fairly complicated set of charts that are going to be very similar. So I'm going to explain this first one in more detail, and then as we go through the others, you'll see a lot of common characteristics. So this upper plot is linear acceleration in G's, and it's over the course of a cold start FTP cycle. And so the blue curve represents what you get in vibration when the engine's running in normal 6-cylinder mode the entire cycle. The orange curve, which often overlaps the blue curve, is what you get when you're running in CDA mode. And so the actual real-time data is this sort of fuzzy stuff that's got a lot of variation to it. The dark lines are a smoothed response to give you sort of an average value of what's happening as you look at the vibration as a function of time. And what you can see is that in many cases, especially here in the middle part of the cycle, the two are identical. And that's at least in part because you're running in 6-cylinder mode a good chunk of this time. But there are places where there's a separation where the CDA response is lower than the normal 6-cylinder active mode. And that's basically where we're running at very light load or idle. And so we have an extended period of CDA operation. So you see that in these two areas here at the beginning of the cycle, and then you see it again here towards the end of the cycle where the average vibration for CDA is lower. The middle plot then is looking at torsional acceleration. And here again, the concept is that you want the torsional acceleration to be below a certain level because experience shows that you end up with NVH issues in the truck when it's above that. And that criteria is basically set for idle and low speed light load operation. When you're running at higher load and higher speed, you normally would exceed this torsional acceleration limit, which is 500 radians per second squared. And again, what you see here is that the two curves, when you looked at the smooth data, the two curves are very similar. That first idle segment, when CDA is active, the first two idle segments here, the amplitude is a little bit higher in 3-cylinder mode than it is in 6-cylinder mode, but they're still well below the limit. And then the behavior when you're operating through the cycle and switching back and forth between 3 and 6-cylinder mode, it's very, very similar. And then the bottom plot here is looking at an engine speed trace, which is in dark blue, and an engine load trace, which is in dark red. And so you can see that, for example, in this section here from 400 seconds to 600 seconds, the speed is relatively high most of the time, but the load is alternating between a positive load, relatively high load, and motoring, so where you're spinning the engine with the inertia of the truck, or in this case with the inertia or with the power of the motoring dynamometer. These green areas are areas where CDA is turned on. And so in this first segment here between 1 and 200 seconds, CDA is on a good chunk of the time. And again, between about 275 and 375, CDA is on most of the time. And in other cases, it's coming in and out occasionally. And so you can look at these plots and compare, what's the speed and load doing, what's the torsional acceleration doing above that, and then what's the linear vibration of the engine doing above that. That's how all these plots that we're going to go through are configured. So here's the response of the FTP hot start cycle. And you'll notice again that CDA has a slightly lower vibration level here in this early part of the cycle. After that, there's almost no difference. And if we switch back and forth between the two, you can see that the vibration level in the cold start cycle is generally higher across the board than it is for the hot start cycle. And the reason for that is when you cold start the engine, the friction of the engine is going to be higher, the oil viscosity is higher because the oil temperature is lower. And so you end up using more fuel to accomplish the same task as you do when you're running a hot cycle. And since more fuel, that means higher cylinder pressure, which means more vibration. And so that's the reason for the difference between these two figures. Other than that, because it is exactly the same speed, load, time history, the results are pretty similar. Here's a look at the low load cycle. So the low load cycle starts off with a lot of speed variation and a lot of load variation, but it's mostly light load. A lot of time you're under 3 bar. And so it's kind of hard to see in this plot because of the way the time has to be compressed. But there's a lot of CDA turning on and off through this period. And then when you get up around 2,000 seconds here, there's a steady period of idle. And so their CDA stays on all the time. And then above that, you see that the torsional vibration amplitude is slightly higher, but still well within the 500 radians per second squared limit. And then you see that the average linear vibration is lower than it is for the 6-cylinder active segment. Then we go back into another period where we have fluctuations in both speed and load. Then towards the end here, from about 4,200 to a little over 5,000, it's mostly idle, and so you see a big difference up here in the vibration levels. And then at the end, there's actually a very brief excursion to relatively high load and high speed, and of course that's on a 6-cylinder firing basis. And the reason for that in this low load cycle is that if you cool off the after treatment and then go to high load, you typically would get a lot of NOx coming through the catalyst without being converted. And so the idea here is to make you keep the after treatment active so that when you do apply higher speed and load at the end of the cycle, that you don't get a big NOx breakout. Here's a look at the 55 mile an hour cruise cycle results. And so here, the engine speed is effectively constant for most of the time period because you're in gear and you're running at a constant vehicle speed. The load, however, is fluctuating pretty significantly. So in some cases, the load is negative. That means you're going downhill. In other cases, the load's quite high where you're going uphill. And in fact, in this case, you can see the speed drops just a little bit because you are going up the hill at 100% load and not quite able to maintain speed. But you also see that every time you're going downhill and you have negative load or light load, CDA comes in. And in these cases, occasionally the vibration you see is a little bit higher than it is in 6-cylinder mode, but they're always in these troughs where the vibration level's at a minimum anyway. And so our judgment here was that this really wouldn't be a factor when you're in a 55 mile an hour kind of cruise mode. So in our test cell setup, we had a couple of resonances that were particularly pronounced when we were operating in 3-cylinder active mode. And that's shown here by this figure that has speed on the x-axis and linear acceleration on the y-axis. And the red curve is the 1.5 order trace. And you can see there's a large spike here at about 850 RPM and a second large spike here at about 1200 RPM. And that represented a 21 hertz resonance of the mounting system and a 30 hertz resonance of the mounting system that were being excited by the 1.5 order firing frequency with 3-cylinder active mode. And so the way to deal with this, or one way to deal with this, is to change CDA modes so that you're not running in 3-cylinder mode when you're on or close to a resonance. And so that's what we ended up doing for the test cell system, was we went to either 2 or 4-cylinder mode to avoid exciting those resonances. And of course, 2 and 4-cylinder mode would also excite the same resonances at a different speed. So there were speeds where it was very unattractive to run in either 2 or 4-cylinder mode. Looking at vehicle mounting systems, which is where most of these engines would be headed, heavy-duty truck mounting systems typically have natural frequencies between 10 and 25 hertz for the 6 rigid body powertrain modes. So the rigid body modes would be motion along the X, Y, or Z axis, or rotation about the X, Y, or Z axis. And the people who design these systems have constraints on them because you can't move the natural frequency of the powertrain mounts in a way that would line up the resonances with resonances of the vehicle structure. So, for example, the frame rails or heavy things that are attached to the frame rails, like fuel tanks and the radiator system and so on. And so ideally what you would like to have is a mounting system that allows you a low natural frequency in roll along the roll axis of the engine, but then allow only higher frequencies for the other rigid body modes. So vertical, lateral, pitch yaw, all those modes. And that would allow the mounting system to accommodate a lower firing frequency without compromising ride or other vibration that the driver would experience. So what we've learned so far is that there are production mounting systems out there that give you good isolation when you're using CDA at idle, and there are others that have a problem at idle. So basically, it's a speed-related thing. The higher the speed, the higher the excitation frequency, the less likely you are to have problems. But you can get into trouble as you come down near idle with some of the production engine mounting systems that are out there. So because of that, Southwest Research and Eaton plan to do some future work in a production vehicle to evaluate what engineering changes are required to ensure good vibration performance in the vehicle with CDA at idle and under low-speed light load operation. And we've got 2 projects set up. There's a joint test program with EPA, which actually should have already been finished, but because of the coronavirus pandemic, the EPA's lab was closed for an extended period of time. And so that's still to happen this fall. And then we also have a joint test program with the California South Coast District to look at the same issue in more detail. And so basically, it's a preliminary investigation of the truck with EPA, and then a more extensive investigation later with South Coast. And what we hope to come out of this with is to provide OEMs with specifications on how to design a mounting system that will achieve good isolation with CDA active, and do it without compromising other things that you care about, like mount durability or other aspects of the mount performance, which would be basically make sure you don't create a situation where you have a ride or a vibration problem due to lining up natural frequencies of the powertrain with natural frequencies of the vehicle. And based on our experience so far, we expect that at least one existing mounting system will need little or no modification to work well with CDA, but there are other mounting systems out there that will require modification. So to wrap things up, we can see that both linear and torsional vibration levels during CDA operation are similar to or often less than levels that you get during normal engine operation at the same speed and load. We don't get any large spikes in vibration during transitions between normal and CDA operation or between different modes of CDA. So, for example, 2 to 3 cylinder or 3 to 4. There may be some opportunity to expand the operating time in CDA by trimming the hysteresis. That's really something we haven't explored yet, but we will probably explore it in more detail. And then, and really, number 2 and number 3 are kind of tied together. If there is a objectionable vibration experience for the driver when you change CDA modes or when you turn it on and off, that would limit how much you would want to do that. And since we didn't find those problems, that we think there's an opportunity to be more aggressive in how often we turn on CDA or how often we switch modes. And then finally, then the lower frequency of vibration that you create when you're operating in CDA can be a challenge for truck engine mounts at low speed. And that'll be the focus of our future work, to define a mount system that gives you good isolation without sacrificing the other characteristics that are important, like durability and ride performance. And I think that's all we've got for the presentation today, and we'd be happy to consider your questions.
Yeah, I agree, Tom. Lots of great information. Thank you for going through that. And you know, by the looks of the questions that have come in, you know, people are interested in learning a little bit more. So if you haven't already done so, go ahead and send us a question. We'll try to get to as many of them as we have time for, but if we don't get to your question, we will get back to you with an email response. So let's go ahead and jump into the questions, okay? So this is your opportunity to engage the experts, as we say. So Tom, first question, have you run CDA on production vehicles? And if yes, what NVH issues did you observe?
So we have, and it's 3 or 4 different vehicles from different manufacturers. And our experience was that one particular vehicle was extremely tolerant of CDA, and we basically could do anything we wanted, and well, with one exception, and it was happy. And so basically it was possible in that one vehicle to operate CDA the way we would like it to be operated for emissions reasons and not have any vibration issue. In the other vehicles that we tested, there was always some operating condition where we struggled to find a way to operate CDA and not have a vibration issue. And it's not across this whole speed load range, but there were certainly points where we had an issue.
Okay, great. Thank you. Here's another one for you, Tom. Can active engine mounts be applied to Class 8 engines or vehicles?
Well, there's 2 answers to that. The first answer is yes. There's no reason why you couldn't. And the second answer is that manufacturers are very unwilling to spend money on engine mounts in North America. We're typically an order of magnitude or more cheaper than the mounts that a European truck manufacturer would use, for example, and those are still passive mounts. So from a financial point of view, active mounts are not very attractive. In my experience so far, I think we can take care of any issues with vibration without going that far. But certainly that would be a feasible thing. It's just the practical cost implications.
Okay. Here's one that has just come in. Can you comment on the torque roll axis? Let me say that again. Can you comment on the torque roll axis based mounting design optimization, as this would be less sensitive to a rolling motion?
And the answer is yes. That if you design a mounting system to be low stiffness for the torque roll axis, but higher stiffness in the other directions. That's exactly what we think is the best approach to achieving good vibration performance in a truck.
Okay, let's see. We got a couple for some of our other panelists here. Jim, what was the criteria for setting the 3-bar BMEP load limit for operating CDA?
Yeah, thanks, Tom. Thanks, Tony. The 3-bar limit, we actually expanded the operation well beyond 3-bar in some of the work we did at Purdue with Purdue and Cummins. And we found that through testing, there was an inflection point around 3-bar where you had enough exhaust temperature above 3-bar, so you really didn't need CDA for the heat there, and you didn't start saving fuel above 3-bar. So what we found is below 3-bar, we could add 100 to 200 degrees Celsius on demand while saving significant amount of fuel at the lowest load, sometimes 50% of the fuel. And through this testing here with NVH, we showed that up to 3-bar and a little bit beyond 3-bar, we didn't have to worry about NVH. So 3-bar and below seems to be our sweet spot for CDA, and that's what we're focused on here.
Okay, thanks, Jim. We didn't talk about this, or I did not see it, but we have a question. How is CDA coordinated with engine braking? I don't know who wants to take that one.
Jim, why don't you take that?
Yeah, I'll go ahead and take that. So engine braking, you don't need CDA for engine braking, so you want to go ahead and increase the friction. You want to slow down the vehicle in engine braking mode, and in CDA you want to reduce the friction and you want to go further. So they're really, you would not be doing CDA and engine braking at the same time, unless we're looking at some more exotic mode of operation that we haven't considered yet. But you're either going to be in 6-cylinder mode, CDA, or engine braking mode, but probably not a combination.
Okay, thanks. Chris, we have one for you. How important is diesel CDA in meeting future NOx and CO2 limits? Kind of a bigger picture question.
Sure, that's a good question, Tony. Within the context of our demonstration work on the Stage 3 engine, it was really an essential lever, I would say. And I think that kind of gets to the value proposition for CDA. If we didn't have to also meet CO2 targets, we could certainly push things to meet NOx only targets. And in fact, during the work, we did develop some engine calibrations to try to reach at low NOx. But the problem with those is that, just to give you an example on the cold start, is, we came up with a cold start calibration not leveraging CDA that reached the targets we needed to reach, but it did so at a price on the cold start of almost 5% fuel consumption penalty, because we have to find some way to add the heat we needed to warm up. With CDA, we were able to reach the same, or in fact, in some cases, a little bit better temperature targets and achieve better warm up, but instead we only had about a 1% delta on the cold start. And so when that was, weighted in with the improvements that we see on some of the other, warmed up operations, we wind up at a fuel consumption neutral standpoint. So when you have to meet both targets, a technology lever like CDA becomes really an essential piece.
Great, thanks, Chris. Here's one that just come in. Does the CDA firing order also have an impact on the torsional orders and their amplitudes?
Yes, and the answer is yes, it does. And so you see in the 3-cylinder mode, your torsional amplitude is primarily 1.5 order. In the 2- and 4-cylinder modes, it's primarily first order and some second and third on top of that.
Okay.
So very similar to the linear vibration.
Right. Okay. So we have time for just a couple of more questions here. How long did it take for the cylinder pressure to decay after the deactivation? On the order of seconds, minutes? And do you anticipate oil consumption to be an issue with current piston ring packs?
Jim, I can take that one if you want.
Oh, go ahead, Chris. Sorry.
Yeah, either way. That's actually something that we looked at during our work, and at least with respect to the engine that we were running, in that case, the Stage 3 engine, which was, again, the 15-liter engine, we generally found, although of course it varies a little bit with engine speed, but we generally found that it was somewhere on, it's numerous seconds, 50, 60, 70 engine cycles, something like that, in that sort of a range. But something that Tom brought up earlier in the presentation was essentially a recharge. And so one of the things that we found was important to implement was essentially a recharge or a rebreathing function, so that periodically, as that in-cylinder pressure decays, you want to replenish that for a couple reasons. It helps to maximize the fuel consumption benefit, but also very critically, as long as you maintain that air charge, it prevents us running into problems with oil consumption.
And Chris, I'll just add to that. So we did some work at Purdue to show the same results on a smaller engine. And the second part of that question is, how long can you stay in CDA? And we found in that work that, even though the pressure is decaying, you can recharge, but you can really stay in it with current ring packs, on the order of 10 minutes. But, for the work we're doing here, we kind of recharged at a certain amount of times on the order of 5 minutes. So it's definitely a long amount of time that you can stay in CDA before you have to recharge.
All right, thanks, guys. Okay, we have time for one more question here, and it's about sound quality. So, Tom, can you comment on the CDA engine sound quality, particularly when it's running on 1, 2, 4, and 5 cylinders?
I haven't personally experienced the one-cylinder mode because that would require going out and running the truck at relatively high speed and then motoring it. But the other modes I have experienced, and it's much more of a vibration experience rather than a sound quality experience. It sounds pretty much normal to your ear. It's just a question of whether you feel anything or not.
Okay, great. All right, thank you for everyone who has submitted questions. Obviously, we don't have time to get to all of them, but we will get back to you. That's all the time we have for today. I want to thank our panel of experts for sharing their knowledge on diesel CDA and NVH. And I also want to remind you that we have additional webinars coming up over the next couple of months. So please be on the lookout for our emails and social media announcements, and join us as we delve deeper into diesel cylinder deactivation. Thanks for watching.